So that's why we did it that way. All right, I'm gonna pull up if I can. Let me see. It's in the course documents. I can't remember where I put that folder. Yeah, if I can get it open. There we go. So we'll let you go first and with your discussion, and I'm gonna pull the paper up so I can be on the screen. Thank God for technology. I was hoping imports. Yeah, it did great. Uh oh. All right, you can go ahead, Sam.
Okay. Um, so what all exactly did you want me to cover? Just what was going
Just
on?
yeah, basically what the overall goal of the paper is, and every time we do this, it's gonna be the same points, like
Okay.
overall
All right.
goal, any specific uh data that you want to discuss that kind of prove the point of the paper, and then any application. But I think in for this, we wanted to show the application. But you can talk about all the overall goal, and then any data you want to bring up, and then any application. Because so the application was we were looking at the VIDIC, and we were asking about like how the VIDIC is actually used in like real time, right? So any what was the overall goal of the paper? That's number one. That's usually gonna be in that first or second paragraph, and then any specific results, and then any
Okay.
application.
All right. Um, uh, you want me to share my screen in case they want to follow along, or
Well,
well,
I got the paper on the screen, so
okay. All right. Well, yeah. In this article, this experiment or whatever, they were trying to control the stereoselectivity or the stereochemistry when using um, this Wittig reaction,
mhm.
and they're normally uh, the traditional method. I believe it yielded mostly Z isomers.
Hmm.
So they were trying to come up with a new method that would control that stereochemistry and produce mainly E isomers. And they there was some method I believe that already existed.
Yeah, the Schlosser method.
Right, the Wittig-Schlosser method using the 1,2-diiodoethane with the beta oxidolylate,
Hmm.
and um, I believe they also use that method, and those results are shown in chart one.
Okay.
Um, and then they ended up trying something different and using iodine, I believe.
Hmm.
Um, and then, yeah, the results from those experiments are shown in chart two.
All right, I'm gonna scroll to chart two. Yeah. Okay. Right here.
Right, right.
Hmm.
Um, and as you can see, um,
Oh wow.
they were able to control, get a little bit more, a little bit better selectivity um, as it relates to the product being more of the e-isomer.
Okay. So for A, what? So R was phenyl. Ah, I see it. So if we look at A, you can see that the R group is an aromatic, and because of that, you get 99 to 1 for the Z or the cis. Well, it'll be Z because it's a tri substituted. And then 51% yield, that's not too bad. And then when you change it to a octal, you can see that in there. Then you get 52% yield, but you get a change in the selectivity from 28, from 1 to 99 to 28 to 72. Okay. And then changing where the iodine is, it looks like they are able to control the selectivity. If you look at C, 6F is 99 to 1 E to Z. And then 6E is also 99 to 1 E to Z. Wow. So I guess it depends on the location of your iodine. Is that what they were proposing? Or is the iodine built into the substrate that they're using to make the illet out of? Because it looks like they made bromoalkenes here and then iodoalkenes at the bottom. That's interesting. But being able to control that selectivity is a big deal, especially for the Vidic. Because under normal circumstances, if you just use, like we talked about Wednesday, aliphatic uh, illets, then it's you get cis, and then you use aromatic illets, and you get trans because of the stereochemistry. But let me use. Go ahead. You can go ahead and what about the application part? I don't want to cut you off.
As far as the application, I thought that that was the application. They were trying to control the stereochemistry or stereoselectivity of it.
Right. Okay. So when you have a method, again, that's the method. And so now you want to take the method and apply it to something
Okay,
that
okay, and then
you can prove, okay, I need this to be trans. And so let me find something that I can synthesize with a trans double bond in it and then apply my method to it to show everybody that it works. Right. That's what this
oh
part is about right here.
yeah, okay. Is that what you were talking about in scheme four?
Yeah,
Where they
fatty acid.
size the fatty acid.
Hmm. So you can see that they have their auto illet out here, and then they're able to they do it with the lithium salt, and then here's your aldehyde right here, and they're able, and look at the selectivity. It's 99 to 1 E to Z, which is what they need. They needed uh this central alkene right here to be Z. I'm sorry, E. My bad. They needed this to be E, right? And so that's how they're proving that their method works by finding a molecule and applying the method to an actual problem, a synthesis problem that they want to solve, right? And if you look at right here where it says the acid 13 is a part of a family of fatty acids containing 5E9Z6 bromodiene functionality, right? And then the purpose is here. Now it may be some minimal biological activity, but that's always the justification. That's how you get money. You stick that in a grant somewhere that we're making these compounds with biological activity. So that's the purpose of saying that. But the actual fatty acid is a natural product, and what they did was they took their method and applied it to that natural product.
Okay, I got you.
So this paper was really basically again an innovation of the ILIT technology that we already know about and the Vedic technology that we already know about. They just took it a step further, and they're able to use these lithium salts to force that stereochemistry to be what they want. But I do want to take an opportunity with this paper to talk about that the Schlosser modification, because see, before, if you took a aliphatic illet like this, and we can talk about that real quick if I can spell it. So what the Schlosser modification allows you to do is it allows you to synthesize trans alkenes from illets that will normally give you cis stereochemistry, right? So if you have something like this, right, this is an aliphatic or non-stabilized illet, right? And so if it's non-stabilized, then you expected to get out the I'm sorry, the cis stereochemistry in your alkene, right? So the Schlosser modification, which is old, 1964, that's when it was first published, and it's in Angavante, page 636, right? What he showed was that you could actually rearrange the illet in situ, right? And so if you take the same illet, well, you can rearrange the oxyphosphate, not the illet, my bad. So if I take these two, uh, take this illet and this aldehyde, and then at low temperature, I treat it with butyllithium, which is a very strong base. And I'll show you what that is in a minute. And then follow that up with terbutanol and I let it warm to room temperature. Right, I actually can get out the trans alkene, which is totally unexpected. Right, but the what happens is the actual oxyphosphatane. So once it cyclizes, um, that's where your rearrangement happens. So that's what the purpose of that base butyllithium is. So let me show you what happens. So here's your so we're gonna do a kind of a, let me not say rearrangement. I'm gonna say modification because it's not a rearrangement in the technical sense. So it's a modification of the oxyphosphatane, right? So let's take that oxyphosphatane. It would look like this, right? And of course it's cis, right? And then There's a lag. It should come up in a second. I don't know why it's lagging. Come on. I'm just writing away. Ain't nothing on the screen. I'm not sure why it's lagging. Let me stop sharing and reshare. Still lagging. Come on, man. This is not thanking God for technology. Technology let me down. Come on. All right. Let's I don't know why this thing is lagging like this. But anyway, this is the oxyphosphate, and then what the Schlosser modification does is it takes the oxyphosphate, and then that base that you treat it with is going to come in and do a proton transfer, right, on this carbon right here, right. So we have that butyllithium. I'm just going to abbreviate it and call it and just call it base. That's going to come in and boom, deprotonate that, right? And so what you end up with is this anion where now you have a pair of electrons in this p orbital, and then now the CH3 is undefined. Well, the group that's attached to substituent is undefined. So then when you add in the acid, right? In this case, it was tert-butanol that you added, right? The H can come from either side, but it's going to add to the uh, front face. So it's going to add here to this face, right? And that's going to cause that substituent to end up being trans or going to the back. So then what your oxyphosphate looks like this now. But now this is going back. This is coming up. You got a hydrogen here, and then you got a hydrogen here, right? Which is really the more stable conformation for that oxyphosphate, with those two groups being trans to one another. The only reason they're cis is because it's under kinetic control, and that cis ring closure happens faster than the trans, right? But under normal circumstances, a trans alkene is going to be more stable. And then so when this breaks down, when it goes through this decomposition, right? Where this pair of electrons comes here, and this pair comes here, then you're going to get out the trans alkene, right? So that Schlosser modification really changed the game. Uh, it changed the game as it relates to being able to control the stereo selectivity of a Wittig reaction, right? Because you can you can if you need a trans alkene, you can just do the Schlosser modification to get it, no matter what type of illet you start out with, right? And then even in this second step, you could when you where you add in the proton, you can add other electrophiles in too, and they will add to that negative charge on that carbanion just like a proton would. Right. So here, let me write that in. That it'll attack the front base. Right. So the whole goal of the Schlosser again is to take the take a illet that would normally give you the cis a cis alkene, and then do this modification by adding in a strong base to deprotonate the oxyphosphatane, and then once you do that, you can just add a proton source in, and that proton is going to convert what was a cis oxyphosphatane into a trans oxyphosphatane. Let me write that up here because that's really the overall. And I'm gonna abbreviate that. All right. Any questions about that? About the Schlosser modification? About anything we just talked about? But yeah, that's a good paper though. The way that that's pretty elegant. The way they were able to do to control that stereochemistry. And Hassan is a good. This is his area, so he's really good. I've been reading his papers there since I was a grad student. All right. Morgan or Jonathan, which one of you want to go next?
I'll go.
All right. Let me pull the paper that I gave that I sent you. Let me pull it and put it on the screen. Uh-oh. Great. Come on. All right. Which you had a paper with the cyclization in it. Total synthesis of, of excuse me, D-acetoxy, 7-D-acetoxy.
Yeah, it was.
I got you. I see it.
Okay.
I just need to match up the DOI so I can pull the right. Well, I can just open both of them. I think it was this one. Yeah, I thought right. So I'm gonna put this in, and I'll combine all this stuff and post it to Blackboard under the notes for the day. Let's see. All right. So go ahead, Jonathan. Give me the overall goal of the paper, any
So,
data,
uh,
and then application.
okay. So basically, they were using marine metabolites obtained from Gregorian and soft corals to isolate euclin and diterpenes.
Mm-hmm.
They did this basically by synthesizing the acetyl cyanine acetate from the glycol pivolate and carbon using a Prince Pinnacle reaction.
Mm-hmm.
So they basically were showing the power of the Pinnacle terminate cation cyclizations for constructing complex tetrahydrofuranus.
Okay.
And they used the Prince Pinnacle condensation basically of the rearrangement of the dinyl 3 with the aldehyde to assemble the boxyclo. So basically, to do to actually get the euclid terpenes to actually go through and synthesize them, basically.
Mm-hmm. So
they use the Prince Pinnacle condensation reaction.
Yeah. So these are the unicellin. You can see over here it's a very complex structure, right?
Uh-huh.
You have this. It's actually a tricyclic system where you got a 6-membered ring and you got a 5-membered ring. Let me change the color on that highlighter. You got a 5-membered ring right here fused together, and then you got this 1, 2, 3, 4, 5, 6, 7-member ring. Right. So you got 3 different rings fused together, but the backbone is that central, like that. Let me see what they call it. They gave it a specific name. Right here, defining reactionary strategy, Prince Pentecost condensation rearrangements.
Yeah, so that's what I was talking about with that.
Yeah, to give that 2-oxobicyclo 4,3-O known 4-ene. Yeah. All right. Go ahead.
Then they so basically, if you look at figure, I thought from what you asked, in figure 18, I thought that would be your elimination reaction, or that's when it occurred.
You said number 18.
Right
here. Okay.
From 17 to 18.
17. Yeah. Let me. Yep. Okay. So 17 to 18. Yes. Here to here.
So is that the elimination reaction?
Yes.
Okay.
So this is 17, this is 18, and we need to see what they did, right? That is where the olefination occurred, but we need to see exactly what they did, because you can see you start out with in 17 with an aldehyde, and then in 18 you can see the first set of reagents is this illite, right? So they actually did olefination with a yeah. Okay. And then they treated that with triflic acid to get to 18. So let's see what they did. That's a good point. You can finish, and then we're gonna come back to this reaction. And then I'm gonna talk about that Prinz reaction too, because that's a pretty important reaction. So was that the last thing that you were gonna talk about, was the olefination part?
Yep, because I was gonna ask more about basically, because in the paper I was trying to figure out how they got that.
How they got to 17?
Yep.
All right, we can do that. Let's walk through. I'm gonna walk you through the synthetic part. Let's go back to the beginning.
I was reading in the paper, it's saying like they use a little alcohol.
Mm-hmm.
And I was thinking maybe that's what
reagents. This is
during that process.
This is a like I was saying earlier, this is a method paper as well as an application paper, because the method is this Prinz Pentecost rearrangement right here, right? And if you look at the uh, the substrate that you do this trans pentacle rearrangement, you always use a diol, which they have here, right? Use a diol, and then you use an aldehyde, and then that's how your cyclization happens, right? There's an intermediate in here that they haven't shown, but the Prince intermediate looks like this. So if you start with this, I'm just going to draw it out right quick. And this is how they set. It's really elegant the way they set this up too. Overman and Macmillan both are legends when it comes to synthetic organic chemistry, especially Overman. He's a legend. They do big things out in California. So this is I'm just going to write the intermediate. And so whatever your aldehyde is in this case, R2, this is what it looks like, right? And then that actually decomposes once you add in the aldehyde. That actually decomposes to give you this right here, right? And then that's the part where your actual Prince cyclization takes place, because what happens is you get this pair of electrons is going to attack here. You're going to attack the aldehyde, push those electrons there, and then the bond right here, because once that double bond breaks, what ends up happening is you end up with a positive charge on this carbon. Let me make my pen a little thinner. You end up with a plus charge on this carbon right here. Once that pair of electrons gets pushed over to attack the aldehyde, you end up with a plus charge on that carbon. And then when that happens, let me just, matter of fact, I can just draw it out here. So you end up with this. I'm gonna draw it a little different than they have it drawn, just to make it easier to see. So that's positive. And then I'm just gonna put all this crap down here, and that's hydrogen right there, right? So then when this attacks right here, right, you get a plus charge here on this carbon. And so this bond migrates over to attack that plus charge. So that's how you get that's how you get the ring, the 5, 6 ring system right there.
Okay.
I'll change colors. So this is gonna attack. Come on, pen. It's gonna attack that carbon right there. So then that's why you'll have 1, 2, 3, 4. Where's that fifth? It's upon plus charge. 1, 2, 3, 4. It's not this carbon right here. Yeah, I'm gonna take that back. So you're gonna have a bond between here. Yes, 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 that's it. So you'll have a bond between these two carbons, and then you'll have a bond between these two carbons. So that's where your 5-member ring is gonna come from. So you get that 5, 6 system. And then once you build that part up, you can see right here, everything else is all like, this is commercially available, right? You can buy this, and then you convert it into a vinyl lithium, which is they did right here. And then this is your other substrate that you're going to add in, which is just an epoxide opening, right? They open up this epoxide, and the PV, all these, when you see that, that's a protecting group, right? It's used to keep that alcohol from reacting with other things. during the process of the synthesis. Right, and then they took this right here, and then they took 6 from up top and converted it to a vinyl lithium. So right here's a vinyl iodide, and then when they got down here, they treated it with tert-butyllithium, so you end up with 6, a lithiated version of 6. So it looks like this. And that's a great nucleophile, by the way. Boom. Right. And then those two are going to react with each other, and that's how you get that coupling that they have shown over here. All right. And then once they get to that point, it's just a matter of doing the cyclization, and this is what they did it with. The prens happen here with that aldehyde. Remember I said up top that the prens, you need you get this intermediate right here when you react that diol with the with the aldehyde. So that's what they did here. And then obviously they didn't show the whole mechanism, but uh, once you add the aldehyde, you get that pren cyclization, and so now they got the whole backbone built. It's just a matter of getting the other uh, functionality in so you can close up the 7-member ring, which they did at the end. All right, so that you can see right here, you can just go through the steps. They epoxidized this double bond and then opened it up with a hydride source. That's what red Al. It's a source of H minus, right? So they open that up to get here, and then do another protection using pivotal chloride. That's what that is, and then tert-butyl dimethyl uh, triflate, silotriflate. So that's what you have here. So you can see that both alcohols got protected, this one and that one, and that's on purpose. All right, all these protecting groups do is keep your alcohols from reacting. Okay, and then they took the alkyne, treated it with 9-BBN, and turned it into a vinyl iodide, which you have right there. And then the second step, uh, they took off the pivotal group right here, and then oxidized it up to a aldehyde. And then that's what, from there, that's why they did the Vidic. And then the last step, they actually just closed the ring up using this nickel technology, where it's kind of almost like a Grignard type technology, where they made they converted the vinyl iodide basically into a nickel nucleophile, and they just attacked right here. So those two pieces attacked each other. Boom. That's how you get this alcohol down here. And then after that, it's just a acylation and a deprotection. This took this in tetrabutyl ammonium fluoride will take off this, and then the acylation part, you can see that happen right here on the OH group. All right, so this is a very elegant synthesis, but the key was that Pran's rearrangement, and it's just like when we were talking about the Claisen and the Ireland Claisen and the Cope rearrangement. It's almost similar to a Cope, but it's not 3,3 sigma tropic, right? It's just a migration of a sigma bond across that system. So we out of time. So Morgan, you'll open us up on Monday with your paper, and then we're gonna keep talking about these olefination methods, and we'll pick it back up on Monday.
Okay.
All right. Any questions about anything? I know this is a lot, but it's good. It's a good lot. This is good because when you look at synthesis papers like this, you get immersed in learning different, different techniques like the protecting groups. We're gonna talk about that another time, but those are very important when you're doing synthesis because if you have a free alcohol, that thing can react and do stuff you don't want it to do. So you just cap it off with some type of silicon protecting group or some other protecting group, keep it from reacting. But we got a whole section on protecting groups, so don't worry about that part. We're gonna learn all that. All right. Like the Baptist church say, all hearts and minds clear.
And Dr. Rocco, did you get my email?
Let me look. When did you send it? This morning or last night?
Nah, yesterday sometime.
And I got to search for it.
It's okay. When you look at it,
Yeah, I'll email you back when I find it because I'm gonna go through these emails today.
okay, no problem. Thank you.
All right. All right. Y'all have a good weekend.